Hello and welcome. This is episode 2 of Pre-Calculus Enrichment Series. Yay. And this time we're going to talk about power functions. You can see some examples at the bottom here. But today I'm just going to go over some even power functions. The next video will cover odd power functions, and then I'll also have an applications video. So let's jump right in. Don't freeze on me. Hold on. There we go. Okay, what are power functions? So it follows this form: y equals k times x to the n, and k and n are both constant. Something I want to clarify is that power functions are not exponential. Exponential functions like 2 to the x, they take a number raised to a variable, versus power functions have a variable raised to a number. So kind of distinction there. But then there's also polynomials. Polynomials are a sum of power functions, basically. We're just going to look at one-term basic power functions. I want to mention that n can also be a negative number. So if n is an even negative number, if we have x to the negative 2, we can flip that, and that's 1 over x squared. And that just has symmetry over the y-axis. So I can kind of draw it here. That's what that looks like. If n is a negative odd number, so if we had, let me erase this. If we had x to the negative 1, that equals 1 over x. And that has symmetry about the origin. So I can also show you that here. If I draw it on the graph, it kind of looks like that. And you're familiar with that from Math 3. I also want to focus on some transformations and key features. So we're looking at domain, range, intercepts, increasing, decreasing, positive, negative, concavity, and end behavior. So some of those terms you might be familiar with, and then some of them you might not know, but I'm going to try to go over all of them. So let's look at an example. Y equals x squared, probably one of the first power functions that you learned without even knowing that it was a power function. And so let's go through all these different key features. Starting with domain, we're looking for the x values that will give valid outputs, and no problems here. Negative infinity to infinity. Usually we watch out for asymptotes or invalid numbers, but we're good here. And I do have a video on domain and range, so if you need to review, you can watch that. Range is going to be the set of actual outputs we get when we plug in our domain. And if we look at the graph, our minimum y value is going to be 0, which is included. And then they go to infinity. So we're going to add that in. Okay, domain and range covered. Let's go to intercepts. So this graph intercepts the y and x axis at the same place, which is going to be at 0, 0. And that'll be true for, I think, all power functions. Intercept at 0, 0. And so let's talk about increasing and decreasing, which you may not be as familiar with. Increasing talks about the slope of the graph over an interval. So if a function is increasing over an interval, it means that the slopes of the function are positive. And so let me show you where that is on here. If we go from 0 to infinity, what I like to do is draw little lines along the graph to kind of represent the slope. So I'm representing my slope here. Oh, those are funky. Oh well. Okay, so those are some positive slopes from 0 to infinity. So that is where the function is increasing. Now we might want to look at where it is decreasing, and it's just the opposite. It's where the slopes are negative. And that's going to be from negative infinity to 0. But we can kind of check it. If I draw my lines, make them a little straighter this time, we can see that they are negative. So decreasing from negative infinity to 0. Now, we want to go over where this function is positive or negative. So positive and negative, you're looking at the signs of the y values, basically. So is the function above the x-axis or below the x-axis? In this case, it is above the x-axis all the time. So positive from negative infinity to infinity, sorry. And as you can see, I'm writing an interval notation. If that's confusing, I would recommend reviewing it because I use it all the time on this channel. Now, obviously, if it's positive everywhere, it's going to be negative nowhere. So almost done. We got 2 more things to look at. One of them being concavity, which I'm going to guess you probably aren't familiar with, but I'll kind of talk about what that means. So there are different ways to look at it. Kind of a simple way is that when a function is concave up over an interval, that means it's like a cup. So basically this graph, it just looks like a bowl. And if it's concave down, we say that's like a frown. So sort of like a hill shape. If you want to think about it in more technical terms, I can show you that too. And this is the way that I like to think about it. Concave up is when, as you move from left to right, the slopes are increasing. So, and that's a really important point. Whenever I'm talking about increasing or decreasing, or whenever I'm like drawing my slopes, you always want to work from left to right. That's kind of a mistake that I tend to make. So it's good to keep in mind. So if we want to test the concavity of this graph, let me start from the left and draw my slopes. So negative, 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 flattening out a bit, positive, 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 positive. So my slopes are becoming more positive. So that means concave up. Now concave down, this graph isn't concave down anywhere, but I can show you what that looks like. It's just going to be the opposite. So my slopes are decreasing over the interval, and it looks like a hill. So here my slopes are positive, 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 kind of flattening out, and then negative, negative, negative. So that would be concave down. And as you can see, it looks like a frown or a hill, however you want to think about it. Now, the last thing we want to look at is end behavior. And that's what's happening to the y values as the x values go to either infinity. So we want to see what the y values do when x goes to infinity, and then also what the y values do when x goes to negative infinity. So if we check positive infinity, I'm looking to the right, and I want to see what my y values are doing. And they are steadily going to positive infinity. So like that. And then as x goes to negative infinity, our y values are still going to positive infinity. So I will add that in there. Okay. One last thing we want to talk about with this graph is what happens when you increase the value of n or you increase the exponent. And so I have an example here. You can kind of tell graphically, it sort of flattens out at the bottom and then becomes skinnier. And that's because with this function, values that are between -1 and 1 So just basically decimals. The more you multiply a decimal by itself, the smaller it's going to get. So near 0, we don't have a whole lot of growth. It's just kind of flat. But once you start plugging in values that are greater than 1 or less than -1, the function is going to grow a lot more than if you had a smaller exponent. So that's why it gets kind of closer to the y-axis. And our key features don't change, but just some graphical differences there. Okay, last thing I want to talk about is when we're changing our k value or our coefficient. With y equals x squared, we have a coefficient of 1, but what happens if I change it to 2? And you can see on the left, the graph becomes skinnier, kind of like in the last example. So when k increases, the graph becomes skinny. And that's because you're multiplying every x value by a factor of 2 now. So the y values are getting bigger, so it's going to kind of increase the growth rate. And what if we decrease k? If we make it 1/2, you can see that it becomes wider. So we're going to have a wide graph. For the same reason, you're decreasing the x values by a factor of 2, so y values are becoming smaller, so it's going to kind of fan out more. And effect on key features, there is no effect. You can tell the graph basically looks the same, it just sort of changes the growth rate. But what if we changed the sign of k? So if we had a -k, and I drew it in purple on the left, the graph is going to reflect over the x-axis. That's because when you put a negative sign in front of the x, you're basically changing the sign of all the outputs. So everything that was positive now becomes negative. Everything that was negative becomes positive. And that's why it reflects over the x-axis. So, okay, that pretty much does it for even power functions. Thank you for watching.